Welcome to Infinite Universe with new interesting episode. The foundation of modern physics is built upon groundbreaking discoveries that have continuously reshaped our understanding of the universe. One of the most significant moments in this journey took place on February 15, 2025, when renowned astrophysicist Neil deGrasse Tyson walked into Google's quantum AI campus. He expected a simple demonstration of the latest advancements in quantum computing, but instead, he witnessed an event that would shake the very core of physics. The development of quantum computers had already marked a significant shift in technology, with machines capable of solving complex problems millions of times faster than classical computers. However, what he saw that day challenged not just computing but the very laws of physics that had stood firm for centuries. This is the story of Willow, a quantum chip that defied conventional theories and forced even the most dedicated believers in Einstein's work to reconsider their understanding of reality. Throughout history, scientific breakthroughs have altered the way humanity perceives the universe. In the late 17th century, Sir Isaac Newton formulated the laws of motion and universal gravitation, which provided a systematic framework to explain the movement of objects both on Earth and in space. Newton's three fundamental laws of motion explained how objects interact with forces, while his law of universal gravitation stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This theory successfully explained the motion of planets, the behavior of falling objects, and countless other physical phenomena. For more than 2 centuries, Newtonian mechanics remained unchallenged, offering a structured and predictable view of the universe. As the 20th century approached, scientists began observing phenomena that Newtonian mechanics could not explain, particularly regarding the behavior of light and the motion of objects moving at extremely high speeds. These observations led to the revolutionary ideas of Albert Einstein, who in 1905 introduced the special theory of relativity. His theory proposed that the laws of physics remain the same for all observers moving at constant velocities relative to one another and that the speed of light is a fundamental constant, unaffected by the motion of the observer or the light source. One of the most astonishing implications of special relativity was the realization that space and time are not separate entities but are instead interconnected, forming a single continuum known as spacetime. This led to phenomena such as time dilation, where time appears to move slower for an object traveling at high speeds relative to a stationary observer, and length contraction, where objects appear shorter in the direction of their motion. Einstein's revolutionary ideas did not stop there. In 1915, he expanded upon his work with the general theory of relativity, which redefined the concept of gravity. Instead of viewing gravity as a force acting at a distance, as Newton had described, Einstein proposed that gravity is a result of the curvature of spacetime caused by mass and energy. Massive objects, such as the Sun, create a distortion in the fabric of spacetime, and this curvature influences the motion of planets and even the path of light. This was a radical departure from Newton's gravitational force concept and was later confirmed by numerous experiments, including the observation of gravitational lensing, where light bends around massive objects, and the precise tracking of Mercury's orbit, which deviates slightly from what Newtonian mechanics would predict. While Einstein's theories revolutionized our understanding of the macroscopic universe, they did not align with the discoveries occurring at the microscopic level. The early 20th century saw the rise of quantum mechanics, a field that introduced a fundamentally different perspective on how matter and energy behave at the atomic and subatomic scales. Unlike classical physics, which operates on certainty and predictability, quantum mechanics suggests that particles do not exist in definite states until they are observed. Instead, they exist in a superposition of states, meaning they can be in multiple places or have multiple properties simultaneously until measured. This probabilistic nature of reality was something Einstein himself struggled to accept, famously stating, "God does not play dice with the universe." He firmly believed that an underlying reality must exist, one that could unify quantum mechanics with general relativity, but despite his efforts, no such unified theory has yet been discovered. The fundamental incompatibility between the deterministic nature of general relativity and the probabilistic framework of quantum mechanics remains one of the greatest unsolved mysteries in physics. As scientists continue to push the boundaries of knowledge, quantum computing has emerged as a new frontier with the potential to transform both technology and our fundamental understanding of the universe. Unlike classical computers, which store and process information using bits that can be either 0 or 1, quantum computers use quantum bits, or qubits, which can exist in multiple states simultaneously due to the principles of superposition and entanglement. This allows quantum computers to perform calculations at speeds that were once thought impossible. Recently, Google and other leading research teams have developed quantum chips capable of solving highly complex problems in a fraction of the time it would take even the most powerful classical supercomputers. The implications of these advancements extend far beyond computation. They have the potential to redefine fundamental scientific theories and challenge long-held beliefs about the nature of reality. The birth of quantum mechanics at the beginning of the 20th century was driven by experimental observations that could not be explained by classical physics. One of the key discoveries was made by Max Planck in 1900 when he investigated black body radiation and introduced the idea that energy is emitted or absorbed in discrete packets called quanta. This groundbreaking concept challenged the classical view that energy is continuous and laid the foundation for quantum theory. Building upon Planck's insights, Albert Einstein, in 1905, proposed that light itself is quantized, introducing the concept of photons to explain the photoelectric effect. This discovery provided strong evidence that light could exhibit both particle-like and wave-like behavior, an idea that further reinforced the need for a new theoretical framework. Further contributions from scientists such as Niels Bohr, who proposed that electrons move in quantized orbits around the nucleus of an atom, and Louis de Broglie, who suggested that all particles exhibit wave-like properties, expanded the quantum paradigm. The mathematical foundations of quantum mechanics were solidified through the work of Erwin Schrödinger and Werner Heisenberg, who developed wave mechanics and matrix mechanics, respectively. One of the most perplexing and counterintuitive aspects of quantum mechanics is the phenomenon of entanglement, where two particles become interconnected in such a way that changing the state of one instantly affects the other, regardless of the distance between them. This strange behavior defies classical notions of cause and effect and has been experimentally verified through numerous tests, challenging our deepest assumptions about reality. Now, with the emergence of powerful quantum computers, scientists are encountering even more profound questions. Google's quantum AI team has been at the forefront of this research, and their latest experiment with the quantum chip Willow has produced results that seem to contradict long-standing theories. If verified, this discovery could lead to a paradigm shift in our understanding of physics, just as Newton's and Einstein's theories did in their time. The findings suggest that we may be on the brink of uncovering a new layer of reality, one that bridges the gap between quantum mechanics and general relativity in ways previously thought impossible. As humanity continues to push the limits of scientific exploration, one fundamental question remains: are we truly capable of fully understanding the universe, or are we merely scratching the surface of a reality far more complex than we ever imagined? Quantum mechanics reveals a fascinating phenomenon known as entanglement, where two particles remain connected regardless of the distance between them. This means that measuring the state of one particle instantaneously affects the state of the other. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen explored this concept in what became known as the EPR paradox. They argued that if quantum mechanics were a complete theory, it would require an unexplained spooky action at a distance, seemingly violating the principle of locality, which states that objects are only influenced by their immediate surroundings. This paradox raised fundamental questions about whether quantum mechanics provided a complete description of reality or if some hidden variables were at play. The EPR paradox challenged the very foundation of quantum mechanics, particularly its depiction of physical reality. Einstein and his colleagues considered a scenario where two particles interacted and then separated. According to quantum theory, certain properties of these particles, such as position and momentum, remain undefined until measured. However, once one particle's property is measured, the corresponding property of the other particle can be precisely determined, no matter how far apart they are. This raised a critical question: how does one particle know the state of its distant counterpart instantaneously? Einstein and his colleagues proposed two possibilities. Either information travels faster than light, contradicting the principles of relativity, or the particles already possess predetermined hidden variables that dictate their properties. The latter suggestion implied that quantum mechanics was incomplete because it did not account for these hidden variables. In 1964, physicist John Bell addressed this dilemma by formulating Bell's theorem. He derived mathematical inequalities that any local hidden variable theory must satisfy. However, quantum mechanics predicts that under certain conditions, these inequalities will be violated. Experimental tests conducted over the years have consistently shown violations of Bell's inequalities, suggesting that if hidden variables do exist, they must be non-local. This means that quantum entanglement allows for instantaneous correlations between particles, challenging classical ideas of separability and locality. These findings reinforce the strange and counterintuitive nature of quantum mechanics. Beyond theoretical implications, the study of quantum entanglement and the EPR paradox has led to groundbreaking technological advancements. Quantum cryptography and quantum computing, both rooted in these principles, promise significant progress in secure communication and computational power. As scientific research continues, the mysteries of the quantum world may unlock unprecedented possibilities, reshaping our understanding of reality itself. Quantum computing is a revolutionary technology that leverages the principles of quantum mechanics to process information in ways that classical computers cannot. Unlike classical bits, which represent either a 0 or a 1, quantum bits, qubits, can exist in multiple states simultaneously, a property known as superposition. This allows quantum computers to perform a vast number of calculations in parallel, significantly increasing their computational power. Another key feature of quantum computing is entanglement, where qubits become interconnected in such a way that the state of one qubit influences the state of the others, regardless of distance. This interconnectedness enables quantum computers to solve complex problems exponentially faster than traditional computers. The potential applications of quantum computing are vast. In cryptography, quantum computers could factor large numbers at an exponential rate, potentially breaking existing encryption systems. In optimization problems, quantum algorithms can evaluate multiple solutions simultaneously, offering advancements in logistics, finance, and artificial intelligence. Additionally, quantum simulations can model molecular interactions with high precision, accelerating medical discoveries and the development of new materials. The theoretical foundation for quantum computing was laid in the early 1980s when physicist Richard Feynman proposed the idea of a quantum computer capable of simulating physical systems that classical computers struggled with. In 1985, David Deutsch introduced the concept of a universal quantum computer, a theoretical model that could perform any computation. By the 1990s, these ideas began transitioning from theory to practice. In 1994, mathematician Peter Shea developed an algorithm demonstrating that quantum computers could factor large numbers exponentially faster than classical methods, posing a potential threat to RSA encryption. Experimental progress soon followed. In 1998, a team led by Isaac Chuang implemented a simple quantum algorithm using nuclear magnetic resonance techniques, marking one of the first demonstrations of quantum computation in a laboratory. By 1999, researchers at IBM and Stanford University successfully created a 2-qubit quantum computer, validating the feasibility of quantum information processing. Recognizing quantum computing's transformative potential, Google established its Quantum Artificial Intelligence Lab in 2013 in partnership with NASA and the University's Space Research Association. The lab, located at NASA's Ames Research Center, became a hub for cutting-edge research in quantum algorithms and hardware development. In 2019, Google made a major breakthrough by achieving quantum supremacy. Their 54-qubit processor, Sycamore, completed a specific computational task in approximately 200 seconds, a task that would have taken the world's fastest supercomputers an estimated 10,000 years to complete. This milestone demonstrated quantum computing's immense potential to solve previously intractable problems. Building on this success, Google unveiled its next-generation quantum processor, Willow, in December 2024. This 105-qubit chip represented a substantial leap forward in the pursuit of large-scale, practical quantum computing. Designed and fabricated at Google's superconducting quantum chip facility in Santa Barbara, Willow was engineered to tackle long-standing challenges such as error correction and computational scalability. One of Willow's most remarkable achievements was its ability to perform complex computations at unprecedented speeds. In benchmark testing, Willow completed a random circuit sampling computation in under 5 minutes, a task that would take classical supercomputers an estimated 10 septillion years. Beyond raw speed, Willow made significant advancements in error correction. Qubits are highly sensitive to environmental disturbances, which can introduce errors in calculations. Historically, increasing the number of qubits has also increased error rates, posing a major barrier to building reliable quantum systems. However, Willow demonstrated an exponential reduction in error rates, marking a crucial step toward the development of practical quantum computers. Willow's groundbreaking performance had major implications for the field of physics, particularly in challenging and potentially redefining established theories. The chip's capabilities allowed physicists to simulate quantum systems with a level of detail and accuracy previously unattainable, potentially uncovering new physics beyond the standard model. Moreover, Willow's success provided empirical support for interpretations of quantum mechanics suggesting the existence of multiple parallel universes. The chip's ability to perform computations that would take classical computers longer than the age of the universe hinted at the possibility that quantum computations might be tapping into resources beyond our own universe. In February 2025, Neil deGrasse Tyson, a renowned astrophysicist and science communicator, visited Google's quantum AI campus in Santa Barbara to witness Willow's capabilities firsthand. During a demonstration, the chip performed computations that defied classical expectations. It maintained coherent quantum states across multiple configurations simultaneously, directly challenging Einstein's principle of local realism. It also completed computations that, according to current quantum mechanics, should have collapsed into a single definite state but instead remained in multiple coherent states. This phenomenon suggested that information processing might be occurring across parallel realities. This revelation deeply moved Tyson, who had spent his career interpreting the universe through Einstein's theories. In a private conversation after the event, he reportedly said, "I'm devastated. I've spent my entire career trying to understand the cosmos through the lens of Einstein's theories. What we witness today doesn't just challenge our understanding of quantum mechanics, it fundamentally changes our perspective on reality itself." Einstein said, "God doesn't play dice with the universe." Well, it appears the universe is playing a far more complex game than even Einstein could have imagined. News of Willow's breakthrough spread rapidly through the scientific community, igniting debates about its profound implications. Some physicists argued that Willow's results provided compelling support for the many worlds interpretation of quantum mechanics. Others remained skeptical, calling for further verification before accepting such a radical shift in understanding. Regardless, the breakthrough opened entirely new avenues for studying time, space, and causality. If quantum computers can harness and retrieve information across multiple realities, our understanding of existence itself may be on the brink of a revolutionary transformation. What else might we discover as quantum computing continues to evolve? The possibilities are limitless.